The topic of this lecture is sequence of function part 1. So we'll cover these points in this lecture: sequence of function, pointwise convergence, uniform convergence, and one example. So let us see the definition: sequence of functions. What does it mean by pointwise convergence? So let Fn be a sequence of real valued function. As we know that there are sequence of real number, sequence of complex numbers, like that. This is a sequence of functions defined on a set E. So we say this sequence of function fn converges to a function f on E if limit n tends to infinity fnx is equal to fx for all x belongs to E. As we know, sequence of real number if converges, then it converges to real number. Sequence of complex number if converges to a complex number. Similarly, if the sequence of function f and x, if it converges, then it converges to some function. Here we are denoting it by fx. So remark, if one holds, that is this holds, then we sometimes say that fn sequence of function converges pointwise to f on E. So let us see one example. Let fnx is equal to x to the power n, where x lies in this interval, close interval 0 to 1. And if you find the limit n tends to infinity x to the power n, and in this case if x lies between 0 and 1, this should be included. 0 less than equal to x less than 1, we get the value 0, and if x is equal to 1, then we get the value 1. In case x is equal to 0, then also the value is 0. So therefore limit n tends to infinity fn converges to function f, which is given by fx is equal to 0 if 0 less than equal to x less than 1, and fx is equal to 1 if x is equal to 1. So this definition of fx we have obtained from these two results we have written. Similarly, let us take example number 2. Let gnx is defined by x upon 1 plus nx, where x lies in this interval. Now if x is, so let us see, if x is greater than 0, then gnx, which lies between 0 and 0 less than gnx, and this is less than equal to x upon nx. From this we obtained this, and this is equal to 1 by n. Why this is so? Because x upon 1 plus nx, if x is greater than 0, then this is less than or equal to x upon nx, and this is equal to nothing but 1 by n. So we got this. And when we take limit n tends to infinity, then gnx is equal to 0 when x is greater than 0. Here we use the squeeze theorem or sandwich theorem, because this tends to 0, this tends to 0. So finally this also tends to 0. Also, if x is equal to 0, then g0 is equal to 0. Therefore, limit n tends to infinity, gn is also 0. So what is the conclusion? We conclude that the sequence gnx converges to 0 on interval 0 to infinity. Now let us see one more example. Let hnx is defined by this nx upon 1 plus nx square. Now let us see where it converges. So if x is not equal to 0, then taking limit n tends to infinity hnx, this will be given by this expression, and if we divide by nx square, then we get 1 upon nx in numerator, and in denominator 1 upon nx square plus 1, and when n tends to infinity we get 0. Also, if x is equal to 0, from this expression we get hn 0 is 0 for each n. So conclusion is that sequence hn converges to 0 on minus infinity to infinity. So by these two example, now we can define pointwise convergence of Fn as follows. This is, we can say, second definition, which is equivalent to the first one. We say the sequence Fn converges to F on a set E pointwise when it is told pointwise converges if for each epsilon, if for each x belongs to E and given epsilon greater than 0, there exists a number n belongs to n such that modulus of fnx minus fx is less than epsilon for all n greater than n. In general, this value of n will depend on both epsilon and x. Also, in general, it is not possible to find an n for given epsilon such that one holds for all x belongs to E simultaneously. So in case of pointwise converges, for every each x and given epsilon, we'll find a n. But this n will depend on both epsilon and x. Now let us see what does it mean by uniform convergence. A sequence fn of real valued function which is defined on set E, we say this sequence converges to f on E uniformly if given epsilon greater than 0, there exists an n belongs to n such that modulus fnx minus fx is less than epsilon for all n greater than equal to n and for all x belongs to E. What is the difference between pointwise and uniform convergence? Here, so remark, here n depends only on epsilon but not on x. That is, we can find a uniform n for all x and for given epsilon greater than 0. So if if fn converges to f uniformly, then fn converges pointwise to f on E. That is very clear. Now let us see one example. Here we will show that gnx x upon 1 plus nx, where x lies in this interval, then gnx converges uniformly to 0 on this interval. This example we have seen in previous slide also. So for if x lies between 0 to infinity, then gnx lies between 0 to 1 by n. And taking limit n tends to infinity, we get gnx is equal to 0 because this goes to 0, this also goes to 0, so gnx is equal to 0. So for x is equal to 0, gnx is equal to 0 for each n. Therefore, we conclude that gn tends to 0 pointwise. First of all, we have proved that it converges to 0 pointwise. Now we'll show gn converges to 0 uniformly. For that, let epsilon greater than 0 be given. We calculate this modulus gnx minus 0, which is given by this, which is clearly less than equal to 1 by n. Now this will be less than epsilon if n is greater than equal to 1 by epsilon. So if we take n which is greater than 1 by n, then we have that if n is greater than n, then gnx minus 0 is less than epsilon. But this implies that gn converges to 0 uniformly. What we have shown here, that for given epsilon greater than 0, we have found the value of n which is greater than 1 by epsilon, such that when n is greater than equal to n, then gnx minus 0 is less than epsilon. So gn converges to 0 uniformly. Now let us see one more example. Let fnx is equal to x to the power n when x lies between 0 and 1. Then here fn converges to a pointwise but not uniformly. So here we will see the difference between pointwise and uniform convergence. So first of all, if 0 less than x less than 1, then limit n tends to infinity fn x, that is limit n tends to infinity x to the power n, is equal to 0. And for x is equal to 1, if we take this limit, then 1 to the power n is equal to 1. So from these two values, these two values 0 and 1, we define the function that fn converges to f pointwise, where fx is given by 0 when x lies in this, and it is equal to 1 when x is equal to 1. Now we'll prove it does not converges uniformly. For that, let us take epsilon is equal to 1 by 2. And now let us suppose fn tends to f uniformly, and we'll get contradiction if we suppose this. Then by definition we can find an n such that for all x belongs to close interval 0 and open interval 1, fnx minus fx, that is modulus xn minus 0, that will be less than 1 by 2. But this will implies xn is less than 1 by 2 for all n when 0 less than equal to x less than 1. And in particular, if we take x is equal to n is equal to capital N, we get xn is less than 1 by 2 when x lies in this interval. Now if we take limit x tends to 1 both sides in this expression, we get the value, this expression we get taking limit both side, we get on the left hand side its value is 1 and right hand side its value is 1 by 2, which is a contradiction. So because if we are supposing this and we are getting a contradiction, so we conclude that fn does not converges to f uniformly. Now let us see this example, that is the last example. Show that hnx, which is given by this expression, then hn converges to 0 pointwise but not uniformly. Let us see how we can prove this. If x is not equal to 0, then limit n tends to infinity hnx, that is this expression, and it is equal to 0, and hn 0 is equal to 0. So hn converges to 0 pointwise on this interval. This is the first result. Now if hn converges to 0 uniformly, then again we take epsilon is equal to 1 by 2 and we'll find some contradiction. For epsilon is equal to 1 by 2, there exists some n belongs to I by definition, such that for all x lies between this, modulus of hnx minus 0 is less than 1 by 2 for all n greater than equal to n. This is by definition. This implies hnx, that is nx upon 1 plus n square x square, is less than 1 by 2 for all x lies in this interval. Now in particular, and this is true for all x. So in particular, let us take x is equal to 1 by n, then hn 1 by n, because this holds. But this is equal to n into 1 by n upon 1 plus n square upon 1 plus n square. That gives 1 upon 1 plus n, that is 1 by 2, which is less than 1 by 2. So 1 by 2 is less than, strictly less than 1 by 2, which is a contradiction. So why this contradiction? Because we are supposing it converges to 0 uniformly. So our conclusion is that hn does not converges to h, which is equal to 0 uniformly. So thank you very much. You can find the link of this lecture in description box. Thank you.